Today, we are going to learn more about the DC generator and how it works behind the scene. First, we need to familiarize ourselves with a few basic elements such as the magnetic flux, Faraday's law of magnetic induction, and Lenz's law. Then, we will look into the working principle of a DC generator to plot the graph of flux against time and electromotive force against time. We will also cover about the electromotive force produced when two coils are used instead of one, and the modifications done to the conventional DC generator to increase the efficiency of the generator. First of all, before we go into magnetic flux, let us understand the definition of flux. Actually, flux can be easily understood by looking at the symbol of flux, which is also known as phi. General definition of flux can be understood as how much substance is flowing through the surface over time. This is a sample model to explain how flux works. Do note that the flux is represented by the number of toothpicks that went past the surface. As we can see, 16 toothpicks went through the surface when the surface is perpendicular to the toothpicks. As we tilt the area, we can observe that only 12 toothpicks pass through, which is lesser than the case before. When the area of surface becomes perpendicular to the toothpicks, no toothpick went through the surface. Now, let us apply this concept to the magnetic field lines. Similarly to the toothpicks just now, when the coil is perpendicular to the magnetic field lines, we can see that the magnetic flux is at maximum as all the magnetic field lines pass through the surface. When the area is tilted, the magnetic flux decreases as the number of magnetic field lines passing through it is lesser than before. As the coil becomes parallel to the magnetic field lines, the magnetic flux becomes zero because none of the magnetic field lines are cut. To find out the value of magnetic flux, the formula given is phi equals BA, where B is the magnetic field strength and A is the area of the coil. The SI unit for magnetic flux is Weber. Based on the formula, we can also say that Weber is equivalent to Tesla meter square. If the area of the coil is tilted, we have to do some resolving by identifying the line that is perpendicular to the surface area of the coil. The magnetic flux of a tilted coil is given by BA cosine theta, where theta is the angle between the normal of the coil, which is the perpendicular line to the coil surface, and the magnetic field lines. If we shift the formula around, we can see that magnetic field strength is given as magnetic flux per unit area. When we divide something over unit area, we are actually finding the density of that particular substance. Therefore, magnetic field strength can be also known as magnetic flux density.
The production of electromotive force due to a change in the magnetic field is known as electromagnetic induction. Electromotive force, also known as EMF, is actually the potential difference produced during magnetic induction. There are two important laws of electromagnetic induction we should keep in mind in order to understand better about DC generator. First, we need to know about Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction explains that magnitude of electromotive force is directly proportional to the rate of change in the magnetic flux. By stating that the magnetic field is changed, what we actually mean is that the magnetic flux is cut by a magnet. The law is applied in the situation of a magnet entering a solenoid. Let's take a look at the simulation below. When the magnet moves into or out of the solenoid, magnetic flux is cut. Therefore, an induced EMF is produced. However, when the magnet stops moving in the solenoid, there is no movement to cut the magnetic flux. Hence, no induced EMF is produced. Now, look closely at the angle of the deflection of the voltmeter. When the magnet is pushed slowly into the solenoid, the angle of deflection is small. However, when the magnet is pushed at a higher speed into the solenoid, the angle of deflection is bigger compared to before. In conclusion, the faster we cut the magnetic flux, the higher the magnitude of EMF produced. On the other hand, Lenz's law states that the direction of current induced is always opposite to the direction of the motion made. Let's take a look at the model below to understand more. When we push a magnet bar towards left into the solenoid, there will be a force of repulsion exerted on the magnet bar that pushes the bar away. We can deduce that the right end of the solenoid gains north polarity, while the left end gains south polarity. Now here is a fun fact. This situation actually obeys the principle of conservation of energy, where energy can convert from one form to another. We are doing mechanical work when we force the magnet inside the solenoid, going against the force of repulsion to cause the change in magnetic flux. Therefore, mechanical energy is converted into electrical energy. Newton's third law also supports this theory. As we can see for our action, there is an opposing force acting towards it. Now, stretch out your right hand and let's do some exercise. Right hand screw rule is used to determine the direction of induced current. Give yourselves a thumbs up for following us until this stage. Your thumb represents the direction of north polarity, while your other four fingers represent the direction of induced current in the coil. We can see that the current which flows down the coil deflects the needle of galvanometer to the right. Once again, we can see that Lenz's law is valid, as the direction of current induced is opposite to the direction of the motion. Similarly, when we pull a magnet bar towards right away from the solenoid, there will be a force of attraction exerted on the magnet bar that pulls the magnet into the solenoid. We can deduce that the right end of the solenoid gains south polarity, while the left end gains north polarity. By using right hand screw rule, we know that the current which flows up the coil deflects the galvanometer needle to the left.
Formula of EMF produced is a combination of Faraday's law and Lenz's law. The formula is given as the product of number of coils in a solenoid and the rate of change of magnetic flux. This part here actually originates from Faraday's law, which states that the EMF produced is based on the rate of change of magnetic flux. Take note that a negative sign is present in this formula to obey Lenz's law, where he stated that the direction of EMF produced is opposite to the change of magnetic flux. Now, let's go into the main topic of the day, direct current generator, which is also known as DC generator. DC generator is used to induce electric field by converting mechanical energy into electrical energy. Here is a diagram of how a simple DC generator should look like. The commutator is the key to recognize a DC generator apart from the AC generator. Its main function is to maintain the direction of induced current in one way. Before we look into the working principle of DC generator, we need to know how to apply Fleming's right-hand rule in order to determine the direction of induced current. Your right thumb points toward the direction of the force, while your index finger points to the south polarity of the magnet. The middle finger represents the direction of induced current. Now, let's look into the working principle of DC generator. Take note that this DC generator is rotating anti-clockwise. The coil is initially facing upwards. When the coil is perpendicular to the magnetic field line, there is no induced current as the side A and B moves parallel to the magnetic flux, and there is no cutting of magnetic flux. When the coil rotates anti-clockwise from its initial position, part A will move to the left when the coil moves in an anti-clockwise circular motion. We apply Fleming's right-hand rule to determine the direction of induced current. So, we are sure that the induced current is flowing in at part A. As part B moves to the right, Fleming's right-hand rule indicates that the induced current flows out the coil. Then, the coil continues its rotation until the coil is parallel to the magnetic field line. Part A moves to the left. Once again, Fleming's right-hand rule tells us that the induced current flows into the coil at A. Meanwhile, as B continues to move right, Fleming's right-hand rule tells us that the induced current flows out from the coil at B. As the coil continues to rotate in anti-clockwise motion, part A still continues moving to left. At this point, induced current flows into the coil, which is similar to the second situation. As part B moves to the right, induced current flows out of the coil. Now, the coil has completed a half circle of 180-degree rotation and returned to its initial position. However, the coil is now facing downwards. No induced current is present at this moment as the side A and B moves parallel to the magnetic flux. There is no cutting of magnetic flux. From here onwards, the coil continues the same path of rotation as the second, third, fourth, and fifth situation. However, the position of part A and B has interchanged. Even though there is some changes, we can still observe that the current always flowing out at the left edge of the coil, while the current always flows in at the right edge of the coil.
Let's try to plot the graph of magnetic flux against time. Using the formula of flux, theta is the angle between the normal to the coil and magnetic field lines. In a set of DC generator, we can tell that the strength of magnetic field is a constant value because we are going to use the same magnet throughout the rotation of the coil. Besides, the area of the coil is also a constant variable as we use the same coil with a constant size. Therefore, we can conclude magnetic flux is directly proportional to the value of cosine theta. From there, we can also say that the graph of magnetic flux against time has a similar pattern with the cosine graph. Before we start, it is important to note that we have to pay attention to two aspects when plotting the graph, which is the magnitude of magnetic flux and the theta. The theta can be determined by finding the angle between the normal to the coil and the magnetic field lines. With the theta, we can just use the formula of magnetic flux, which is BA cosine theta, to find the magnitude of magnetic flux. At the beginning of rotation of coil, as the angle between the normal to the coil and magnetic field lines is 0, in other words, the coil is perpendicular to the magnetic field lines. From the cosine graph, we can see that the value of cosine theta is maximum when theta is 0, which makes magnitude of the magnetic flux to be maximum as well, using the formula of BA cosine theta. Looking how the coil cuts the magnetic field at this point, we can also tell that the magnetic flux is maximum as the coil intersects with all of the magnetic field lines. As the coil rotates and part A moves towards left, theta increases. From the cosine graph, we can see that the value of cosine theta decreases when theta increases within the range of 0 to 90 degrees. Therefore, the magnitude of the magnetic flux decreases too. From the diagram, we can also see how the magnetic flux decreases because the number of magnetic field lines cut by the coil is lesser than before. When theta is 90 degrees, where the coil becomes parallel to the magnetic field, there is no magnetic flux as the coil does not cut the magnetic field lines. Here, we could see that region A is still moving to the left as the coil continues to rotate. Theta increases within the range of 90 to 180 degrees. We can see that the number of magnetic field lines cut by the coil increases. Therefore, magnetic flux increases. However, the magnetic flux is negative because by substituting the values of theta into the formula of magnetic flux, it shows a negative value. Therefore, it is accurate to say the magnitude of magnetic flux increases negatively as the angle increases within 90 to 180 degrees. When theta is 108 degrees, it is similar to the situation 1 as the coil is also perpendicular to the magnetic field lines. Therefore, the magnitude of magnetic flux is the same. However, the value of magnetic flux is minimum because the magnetic flux is now negative due to the substitution of theta equals to 180 into the formula. Next, theta increases from 180 to 270 degrees. From the diagram, we can tell that the number of magnetic field lines cut by the coil is lower than before, so the magnitude of the magnetic flux decreases. But since the substitution of values of theta into the formula shows a negative value, magnetic flux is negative. Therefore, we can see that the point on the graph is higher than the point in situation 5. When theta is 270 degree, the coil is parallel to the magnetic field lines. The magnitude of magnetic flux is zero because no magnetic field line passes through the coil. After that, when theta increases from 270 to 360 degree, the magnetic field cut by the coil increases, so the magnitude of magnetic flux increases. At 360 degree, same as situation 1, the magnetic flux is maximum again as the coil is perpendicular to the magnetic field lines. Now let's recall back the formula of EMF. If you remember clearly, the EMF formula is given by the change of magnetic flux over time with negative sign. This means that the negative gradient of the magnetic flux over time graph is actually the value we need to plot the EMF graph. From 0 to 90 degree, we can see that the value of gradient is becoming more negative as the slope is tilted downwards in an increasing manner. However, the rate of change of steepness or gradient slows down when approaching to 90 degree. Based on the EMF formula, we have to take the negative value of the gradient as the value of EMF produced. So the values of this gradient will turn into a positive figure. To reflect these values into the EMF graph, we'll draw a positive graph with a slight curve. Then at theta equals 90 degree in the flux graph, we can see that this is an inflection point, which is the change in concavity in flux graph. We'll then translate this into the maximum point when plotting the EMF graph. After that, on the flux graph, we can see that the value of gradient is slowly decreasing, so the EMF graph will have a declining slope after joining the points together. As the DC generator has a commutator to maintain the direction of induced current, no negative EMF is produced because there is no change in direction of induced current produced.
First, let's take a look at the DC generator below. Scientists have found a way to modify the DC generator to increase its efficiency by using 2 coils instead of 1. Right now, what changes can we observe from the EMF when these changes are made? Actually, we can understand this better if we look at the EMF produced by these 2 coils separately. So the main idea is that we have to realize coil A, it begins at a position perpendicular to the magnetic field line, while coil B, it begins at the position parallel to the magnetic field line. When the coils begin to rotate 90 degree clockwise, EMF will be produced as shown in the graphs below. From the graph below, we can see that the 2 coils will produce a graph with a similar pattern. But due to the difference in starting position, they will have different EMF production at the same moment. When we combine the 2 graphs, this is the EMF against time graph for a 2-coil DC generator. So our main concern is that how does this modification improve the conventional DC generator with 1 coil? Well, let's compare the 2 graphs. As we can see in graph 1, a single coil will produce a weak and fluctuating EMF output. By adding 1 more coil to the DC generator, a smoother and more stable output of EMF can be produced. We should keep in mind that the main advantage of using 2 coils DC generator is to constantly maintain the induced EMF at high level as indicated by the green region. Also, the magnitude of EMF produced will not fall below the green region. Notice that the gradient of EMF in graph 2 is more even as compared to the one in graph 1. The EMF output in graph 1 is lumpy as it was raised to a maximum and dropped back to 0 in each half turn. However, the induced EMF, which is the green region in graph 2, it will never go all the way down to 0 as in graph 1. The ever-fluctuating EMF is known as the pulsating voltage. In the recent years, scientists have been working out ways to modify the conventional DC generator to improve its function and efficiency. So, before we dive into the changes made on the DC generator, it's crucial for us to understand the parts on the DC generator which will be adjusted. This is a simple model of how a conventional DC generator should look like. So first, the outer frame of the DC generator is called a yoke. It acts as a protective shield for the internal components of the DC generator and also provides mechanical support for the poles. The field magnet is attached to the internal walls of the yoke. It is actually made out of a pole coil with wire windings known as pole coil around it. Its main function is to spread out magnetic flux in the air gap inside the generator. Next, the armature coil is similar to the function of a coil. It is rotated to cut the magnetic flux and produce EMF. A commutator is also present to produce a one-direction EMF. First, let's look into the modification that is done to the pole core. In conventional DC generators, magnets are not used anymore to produce magnetic flux. Instead, they use current-carrying wire coils to produce magnetic flux so that the strength of magnetic field can be controlled by changing the current input. Besides that, the armature coil is made out of laminated sheets of silicon steel material instead of solid iron. This material is used to provide high resistance path and reduce the flow of eddy current, as current is less likely to flow in high resistance path. Eddy current is a source of waste energy that is produced by magnetizing the armature core to produce magnetic flux. By reducing eddy current, we can reduce the heat generated by eddy current and increase the overall efficiency of the generator. Not only that, holes are also punched into the thin layer of silicon steels that make up the armature core. The holes are known as the air ducts. The design is important in ventilating the generator and preventing overheating of this machine. Last but not least, bearing is also used to provide a smooth movement of the armature core.